Okay. So last lecture was meant to be a fairly gentle introduction to some of the ideas which form the conceptual underpinnings of this class. We're going to get to metric spaces, the definition today, I hope, at the end of the lecture. But to begin with, we want to finish answering the question which arose at the end of last lecture. So let me just quickly reload into your brain last lecture. So we were discussing a sort of abstract plane which was coordinate free. There were two observers situated at the same point in the plane which had their own coordinate systems. The coordinate systems were related by a rotation of an angle theta. That meant that the two observers write down different pairs of numbers, different measurements for the same point. And then we're interested in, well, which quantities calculated from those coordinates are, in a sense, shared among the observers. That is, they agree on their values, which is the same as to say that f is coordinate independent, or that f after a rotation is the same as f. Okay. Well, this was the same, remember, as saying that f of m1 of x is equal to f of m2 of x for all x. Okay, so that was what I meant by coordinate independent, and then we finished by characterizing the coordinate independent functions as those which depend only on the length. Okay, the length was the prototypical example of such an f, and in a sense it's the only one, because every other such one is obtained from the length. Okay, so, well, that's well as may be, but more interesting is the case where there's 2 points. So I finished with the following question, which we'll now answer. Okay, question. So which functions of a pair of points are coordinate independent I only defined coordinate independence for a function f of this form, but there's an obvious analogous definition for a function which depends on two inputs, i.e. g after r theta cross r theta equals g for all theta. So this is one way of characterizing what I mean by coordinate independent, and it's just a statement that this diagram commutes. Okay. To say that this diagram commutes, remember this was terminology I introduced last lecture, is to say exactly that this composite is equal to g. Or equivalently, it's the same as to say that g of m1 of x comma m1 of y is equal to g m2 of x m2 of y for all x, y in R2.
Is it Rn or R2?
Oh, thank you. Yeah, thanks. Yeah, I meant R2 here. Yeah. Here as well. Yeah, thank you. Okay, so the fact that those two are equivalent is an easy exercise. You should think about it. So now let's answer the question. So which g's are those? Okay, so the first thing to note is that it's a little awkward to, well, so maybe I'll draw a picture first of all. Maybe I don't have colors here. This was observer 1. Here's observer 2. So now I'm talking about 2 points. There's x. Oh, well, there's another mistake on the board. I apologize. M1, that is assigning measurements to a point, but it's assigning those to points in x, not to vectors in R2. Right? So this was a mistake. So this picture here is meant to be this sort of abstract plane without a coordinate system. Those two observers impose a coordinate system, and now they're trying to talk about this pair of points. It's a sort of a little awkward, I mean, not difficult, but just awkward in a lecture which has to fit into 50 minutes, to deal with the special cases where either x or y or both are actually at the origin. It's kind of irritating. So for that reason, I'm going to actually answer a slightly, I mean, just a technically easier question, which is the following. So by the origin in x, capital X, what I mean is the point where both observers are sitting. So let's assume that we only want this condition. We only ask for this condition for those kinds of pairs of points. So we ask which functions. Well, that means that G only needs to be defined away from the axes, right? So which functions G satisfy that criterion? Where Z is just the set of points where either of them is 0. So let's say R2 cross the 0 vector, union the 0 vector cross R2. Okay. And again, that's equivalent to this diagram commuting where I take out Z. Notice that the rotation matrix, when it operates on a pair, never sends non-zero vectors in R2 to 0 vectors. So this is a map between those two sets. And the condition over there is the same as that diagram commuting. Okay, so what I'm going to answer is actually this slightly modified form of the question, but as I said, it's actually, I mean, it's got no less content, really. Okay, is it clear what I'm trying to do? Any questions? Yeah.
Would you rather load this thing? Yeah.
Oh, this thing, sure. That's a good question. I will try. Yes.
Even up here. Yeah.
Yeah. Is that sufficient?
That's correct.
Yeah. Okay. Any other questions? So, is it clear what I'm trying to do? Yeah? Okay. So feel free to have a guess for yourselves what the answer has to be, right? So in the case of one variable, what I found was that the only real function of that form was the length. Now I expect to find something more than just the length, and you can form an educated guess as to what that is. Okay, so lemma. This is star. The diagram star commutes for every theta if and only if there is a function h such that okay, so what's the answer? What's the new thing that I'll find that I didn't find in the case of the F's last lecture? What's the new quantity which pops up as soon as I talk about pairs of points? I heard distance. Distance we already discussed, right? Angles, yeah. Okay. So, of course, given a pair of points, right, the distance from the origin where the both observers are sitting to both of those points, that is the distance to x and separately the distance to y, that's something both observers will agree on, right? Because we already discussed that. That's not involving pairs of points, it's just a single point. The only quantity which they can possibly agree on, which is invariant under rotations of their coordinate system associated to the pair, is the angle between them. Okay, so that's what this lemma says. So conceptually, I think it's absolutely obvious this is the case, and then it's just a matter of going through the rigmarole of proving it's true. Okay, so this is length 1, this is length 2, this is the dot product. Okay, so such that G is equal to h of the length of V, the length of W, V dot W. Now, okay, so let's prove this. So we have to prove two things, right? I have to prove, first of all, that if I take any such function h and construct the function on the right-hand side by feeding in the lengths and the dot product, I get a function g which makes this diagram commute. That is, it's coordinate independent. That's just a calculation, so let's do that first. So suppose that we took a function g which was of this form. That is, it was h composed with the function which takes the norms of, well, suppose g has this form. So we need to show that theta commutes. All right. So that is, we need to show that if I take a pair of vectors, VW, I rotate both of them, then I apply G, it's the same as applying G. So I need to show that G of R theta V, R theta W equals G of VW, and I need to show that for all theta and for all V and W. For all theta, because I don't want to fix a particular angle between my observers. This is for a generic pair of observers related by rotation. Okay, so we'll just calculate, right? Let's calculate the left-hand side and see that it agrees with the right-hand side. The only content here is really that the dot product is independent of rotation. If you rotate both the vectors inside a dot product, you get the same number. Okay, so let's just see how that goes. So what is G? Well, G is, by definition, I'm hypothesizing that it has the form on the right-hand side. So this is h of the length of R theta V, the length of R theta W, and the dot product. Okay, so as we discussed last lecture, the rotation matrix doesn't change the length of a vector. So this is the same as h V W. So I just need to analyze this dot product. Okay, but taking the dot product of two vectors, and my vectors are column vectors, right? The dot product is obtained by transposing the left one and multiplying it with the right one, right? So R theta V, maybe you guys can't actually see that, right? Dot R theta W is the transpose now when I write R theta V, R theta was a function from R2 to R2, right? So I could write R theta of V, that would be the functional notation, but I'm committing a sort of collapse of notation. So R theta also stands for the 2 by 2 matrix, such that evaluating this function on V is just left multiplication by that matrix. Okay, so I'll just write either of them, they're synonymous. Okay, so this is really a matrix multiplication. I take the transpose and I take the multiplication just as matrices, but the transpose is anti-commutative, or rather, okay, that's that guy. But if I take the transpose of that rotation matrix, that's swapping the minus sine theta in the top right with the sine theta in the bottom left, and sine is odd, so that's just really r negative theta. Okay. And we know that rotating by, the sum of angles formula says r psi times r theta is r psi plus theta. The angles are in the subscript there. So this is r of theta plus minus theta. So that's just r0, which is, of course, the identity matrix. So that is just v dot dot. Okay. So that shows that this guy here is equal to h of the length of v, the length of w, and then the dot product, but that's just g of vw. Okay, so that direction has been proved. If g has the structure of the right-hand side, it's h composed with that 3-tuple, then it does have the property that this diagram star commutes, that is, it's coordinate independent. Okay, so now let's move on to the reverse direction. Any questions about this part? Okay. Okay, so in the other direction, so let's suppose we have some function g which has the coordinate independence property. Okay, so what have I got to do? I've got to produce h, right? Such that g is equal to h composed with that stuff on the right-hand side. So let me tell you why it's true, and then I'll write down the formula, which doesn't look quite as transparent as the informal argument. Okay, so I've got a function g. It takes in a pair of points in x and outputs a number. And if I rotate both of the points by the same amount, it gives me the same number. All right, so if I'm given a pair x, y, I can just assume one of them lies on the x-axis of the first observer, right? Because I just rotate the problem until, these guys sit here. Let me prioritize observer 1 for a moment. Apply the rotation, which gets y to sit on the x-axis of observer 1. Well, g has the same value because it's invariant if I rotate both the vectors the same amount. So, okay. So I might as well assume that that's the case. Now, if I take away the lengths of, well, this vector which lies on the x-axis, if I factor out that information, and I factor out the information of the other vector x which has been rotated, well, all that's left is the angle that is made between the x-axis of observer 1 and the second vector which wasn't laid on the x-axis. So that's the argument. So more precisely, let's define a function h by the following formula, which just is really what I said, but spelled out. This is a two-part definition. So the first part definition says, as long as this formula makes sense, that is, as long as the quantity in here is non-negative, which is what that says, then take that, right? So I take this column vector, I take alpha form a column vector, I take beta, gamma, alpha form this column vector. Alpha is guess the way I set it up. See, I don't have to worry about alpha being 0 because of the z, right? That was the whole point of the z. So I'm ignoring the case where x and y are, so alpha, beta here are positive, right? Because I ignored the points, the case where x or y could be lying at the origin. So h of alpha, beta is this. And in the other case, I just take, anything I like. Okay, this is very important. 1, 2, 3, 4, 5, 6. Okay, it doesn't matter, as you'll see. So just define it any way you like on the rest of the values. All right, so let's see why that works. So I claim that for all VW in R2 and all theta, that we have G of VW equals to H of the length of V, length of W, dot product. Okay, so just to reiterate the logic, we started with G, we defined H using G, and now I claim this relationship between the G we started with and the H we constructed. Okay, so we call this equation dagger. So note, the left-hand side and right-hand side of dagger are both functions on R2 cross R2, taking away, that's the alpha beta being 0 part, invariant under R theta cross R theta. Right? So what do I mean by that? They're both functions which take their inputs from this set. If I precompose with this function, which goes from this set to itself, I get the same output. Right? I mean, for G, it's the statement of that diagram commutes. That's what I mean by R theta cross R theta invariant. And the same is true for this H on the right-hand side. Why? Well, because if I rotate both V and W as the inputs to the right-hand side here are a pair of vectors, if I rotate them both by the same amount, well then all three of these quantities don't change. The third one is what we just verified. So if the three inputs to H don't change, then the output of H doesn't change. Okay. So both the left and right-hand side don't care if you take V and W and rotate by theta. Which means if you want to prove they're always equal, you can reduce to the case which I mentioned earlier, where one of the vectors lies on the x-axis. Yep. So that is, we just need to prove this equality in the case where V is of the form alpha 0t, that is the second coordinate of V is 0, and where W, so that's the one that I've rotated to the x-axis, right? And the other one can be arbitrary. It can be anything it likes. So I just write down an arbitrary vector here. That's beta cosine psi, beta sine psi, where beta is positive and psi is some angle. Okay, that's the generic one, the one that's not left fixed. Okay, so we just have to prove this equality dagger in this special case. So then let's do that. Okay, but then H of this stuff is H of alpha. Well, the length of that is beta. And the dot product is just alpha beta cosine psi. Okay, so let me call that quantity alpha beta cosine psi gamma. Right. So that's what H of that pair is. Now let's evaluate G. So G of VW. So that's G of alpha 0t, and then, well, W, but let me write W as alpha beta cosine psi on alpha. I mean, I didn't do anything, right? And beta sine psi, well, sine psi is the square root of 1 minus cosine squared psi, right? So okay, so that's not saying, that's not, I didn't do anything. I just rewrote the inputs to G. But in terms of gamma, I mean, what's this? This is gamma on alpha, and this is the square root of beta squared minus gamma squared on alpha squared beta squared. Oops. But that's how we defined, right, if you take the beta inside, that's how we defined H. So that is H of VW. Okay, so I mean, when you write out the formula for H, maybe it seems like something happened, but really nothing happened. This was just the original informal argument. You just sit down and you write it down. That's what you get. Okay, so this proves that the left and right-hand side of dagger agree on these special class of pairs, but that's enough to prove they agree on all pairs because of the argument about rotating the pairs by the same angle. Okay, so that completes the proof, right? So we've proven both directions of the lemma. Okay, any questions on that part? Okay, so what's the upshot here? Maybe I'll just say it. So the upshot is that the only meaningful, aka coordinate independent quantities that you can associate to a pair of points in the plane, there's really only three, right? The length of the first thing in the pair, the length of the second thing in the pair, and the angle between them, or their dot product. Right? That's what that says. Notice that this isn't symmetric, right? We really mean ordered pairs of points in the plane. Maybe that's a slight detail. Okay, so what we discovered then, so why did we get into this discussion in the beginning? Well, we were discussing last lecture the various kinds of abstractions which take out some of the structure present in Rn and then package it as a separate notion, right? Inner product space, metric space, vector space, and so on. And the question was somehow, well, why do we have all these different notions, and B, when do you use which one? The reason why they're used in different parts of mathematics, different abstractions are used in different sort of settings, is explained in some sort of micro form by this lemma. So the appropriate abstraction for this situation, by situation I mean these two observers related by rotation communicating about their measurements. Well, this lemma says that the appropriate abstraction is that you should allow yourself to talk about lengths, and you should allow yourself to talk about angles or dot products, right? Those are the only two things that both observers will agree on. That's the sort of little universe of discourse that they should engage in order to have meaningful discussion, right? In order to calculate the same quantities. So, okay, so if you look back at that list, the abstraction which knows about lengths and angles is the idea of inner product spaces. Okay. So this suggests a sort of, let me just say connection between the group of symmetries which is given by the rotation matrix. So this group is called SO2. Maybe we'll discuss SON and ON a little later in the course, but just to read out what the letters stand for, this is the special orthogonal group. The group of 2 by 2 real matrices which are orthogonal, that is, their rows and columns form orthogonal vectors, and such that the determinant is 1. That's what the S means, special. Okay, and those are just the rotation matrices. The point of view we've adopted is of looking at observers whose measurements were related or invariant under SO2. And what we arrived at was extracting out this structure of an inner product space. Okay, so I don't want to take that too far, but there is, in fact, some sort of meaningful connection between symmetry groups and the various kinds of abstractions that we have for notions of space. I explain that a little more in the notes, particularly if you have a physics background and you've done thermodynamics or you have some interest in things like Noether's theorem, you'll get a kick out of that, I think. So check the notes. Okay. So that finishes what was supposed to be lecture 1.